We've been talking about which mechanisms a reaction would go. SN1, SN2, E1, E2. But we need to put all of that information together when we're deciding which particular mechanism might happen. And we should start off by making sure that we have a suitable leaving group. We should have one that's at least as stable as fluoride. If we don't, then there will be no reaction. And sometimes it's abbreviated NR for no reaction. Next, we need to consider what is the type of carbon that we have. First, the carbon that the leaving group is bound to should be sp3, hybridized. Next, we can examine whether it's primary, secondary, or tertiary. And we can use this to help rule out a particular mechanism. So, if we have a primary carbon, there's no way that we could have an SN1 or an E1. Essentially, it's going to be very difficult to form that carbocation intermediate. So we will not see SN1 or E1. Let's skip secondary for a second. Now, tertiary carbons will not allow for SN2 because it needs to attack from the back side. It will allow for all of the other mechanisms. E1 and E2 are allowed because we're just abstracting a hydrogen, and so the steric hindrance is not really a problem for the E2 mechanism. And then if we have a secondary carbon, all of these reactions are possible. This is where we'll have the most trouble deciding which mechanism it can be. Because, again, we have to consider all possibilities. At least in a primary or a tertiary carbon, we can eliminate some of the possibilities from consideration. Next, we need to evaluate the nucleophilic strength or the base strength, depending on whether we're doing a substitution or an elimination. If we have a particularly strong nucleophile or base, that would promote the bimolecular reaction. Similarly, the concentration of the species. If we have concentrated reagents, that's more likely to, for the attacking species, it's more likely to promote the bimolecular reactions. Our leaving group ability. If we have still a suitable leaving group, but not the best one, then that would favor the bimolecular reactions because that attacking species will help the leaving group leave. And if we have a really great leaving group, then that will favor the unimolecular ones, the SN1, the E1, because that first step is leaving group leaving on its own, and if we have a great one, then it may go that way. We also need to consider solvent effects. Is it aprotic or protic? When we have a protic solvent, it tends to favor the unimolecular reactions because we're forming that carbocation intermediate, and this is a little bit stabilized by a protic solvent. Now, after we've considered all of these effects, if we still have a tie between a substitution reaction and an elimination reaction, we'll use heat, which is sometimes abbreviated as a little triangle symbol, like a delta, to break the tie. Elimination reactions are favored when the reaction is conducted at a higher temperature. Substitution is favored when it's conducted at a lower temperature. We'll make the assumption that it's not conducted at a very high temperature unless we have the heat symbol on the reaction. So now that we've discuss this little bit of review here, and we're trying to bring this all together, we will consider some examples. So let me get some here that I've prepared. So I've prepared a few examples, and the first few are ones that should be relatively simple to decide based on some of these factors that we've already discussed. So if we look here, we've got a primary carbon that the leaving group is attached to. That is going to mean that we cannot do either E1 or SN1. This is going to have to be SN2 or E2. Then we need to look at our attacking species. Now, if we're not told that this is a dilute reagent, we can assume that it's concentrated. And if we look here, this is cyanide. This is a pretty good nucleophile. In fact, it's a good nucleophile. And it's an okay base. It's not that great. So, adding up these factors here, we have a primary and we have a good nucleophile and then not so great base. We're going to get substitution via the SN2 reaction. And our product would be this, nitrile. And we'd also have some sodium iodide in there. This is going to be SN2. And that was a little bit easier to decide because strong nucleophile and a primary carbon. Next, let's look at this one. Here we have a tertiary carbon, and we have a weak everything. This is water. It's not a particularly strong nucleophile. It's not a strong base or an acid for that matter. So it's just kind of very middle of the, it's water. It's not that strong either direction. So now we have to decide, is this going to be a elimination reaction or a substitution reaction? Well, this isn't a particularly good base. It's a little bit better nucleophile. And we're not heating this reaction. If we were heating it, then I would say, well, that might be an elimination. But we've got a tertiary, we've got a nucleophile here. This is going to be SN1 because we've got a good leaving group. This is going to leave off, make our carbocation intermediate. Then we'll have our nucleophile come in and attack. It's a little bit easier for that to happen. And we should end up with the alcohol. And some HI. All right. Now, here's some that I've included heat. So these are going to be probably elimination reactions. And I've chosen things that are a little bit better bases too. So a very similar substrate to up here. This time I've got a very strong base. And this is not a very good nucleophile because of the bulkiness to this. So this is going to be an elimination reaction, plus we're heating it. And it's going to be E2 because this is a primary carbon. And for primary carbon, we've just got to go with the bimolecular process because we don't want to go through a carbocation that's primary. That would be unstable. And then we'll also make the other side products here. Or it's not really a side product. The other products. Next, we've got an example of E1. And this is E1 because it's tertiary. we've got a base, it's not a particularly good nucleophile, and we're heating this, we're going to deprotonate something here. So we'll just draw that product plus the other things that we're going to make here too. So these weren't that hard to decide, especially when we're choosing primaries and tertiary carbons. And when we're choosing some of the strongest bases out there. Now let's move on to something that's a little bit harder to decide. Secondary carbons. These are where we have to really make some judgment calls and pay attention to all the effects. So most of these are chlorides. I've got an alcohol in here. The leaving group is okay, but it's not amazing, right? If we had amazing leaving groups, that would favor the unimolecular ones. But we may still have a unimolecular reaction occasionally here. So here's a secondary carbon. And I've got a pretty good nucleophile, but this is also a decent base. And I can see here that I've got a polar aprotic solvent, DMSO. It looks like this, dimethyl sulfoxide. So there's no protons on there that can easily come off. So this is an aprotic solvent. Aprotic solvents tend to favor the bimolecular reactions. And this is a good nucleophile right here. It's also a good base, but it's not sterically hindered. And this is a secondary. So putting all this together and assuming that we're not heating this reaction very much, this would likely go SN2. Based on all of those factors. And our product is going to be the flip of this one. So that's going to be going behind. And then we have that. Plus some potassium chloride as another product. All right. Next, let's look at this reaction here. Now, we've changed things. First of all, this is a tertiary, so it's not going to be SN2. But the question now is it going to be an elimination reaction or not? And I suspect that we'll get some elimination products from this. But we'll probably have more from the nucleophile here. This is a fairly strong nucleophile, but now we've put it in protic solvent. So that's just another kick in the direction of SN1, because this protic solvent, that's going to reduce the nucleophilicity of this particular species. And again, we've got a tertiary here. So I suspect that the most common pathway for this is SN1. Now, if we go SN1, we're going to lose the stereochemistry here. So I'm going to just draw these as racemic. You know, let's skip down to this one because it's a very similar substrate. It's the same substrate, slightly different conditions here. Here we've eliminated the really strong nucleophile and we've added heat to this reaction. So when we do that, we should expect that this is going to be an elimination, but it's not a particularly strong base. So this is likely going to be E1. And when we do E1 for this reaction, we're going to get a bunch of products. So we're going to get that one, and we'll also get one where the double bond is here. And we're going to get the corresponding E isomers as well. So, well, this one is E, but we'd get the one that's the Z isomer. And same here, we'd get the other isomer. You get that one as well. So you can see that an E1 reaction suffers from selectivity a bit. And we don't have a difference in substitution around the double bond, so each one of these products is going to be fairly likely to form. But the point here is that we have a tertiary carbon. That said, it could still go either elimination routes, but since we have a weaker base, it's going to go E1 rather than E2. All right, we've got another one up here, which is another elimination. We're heating it. This one is a secondary carbon, but we have an acid. So this isn't a particularly strong base, and we can assume that there's going to be some water floating around in the solution, just because the phosphoric acid, generally, you've got to dissolve that in water. So that will be our base. That's going to be also E1. But we won't suffer from as many different options because we have this as a ring. So we can really only deprotonate right here. And since it's in a ring, it can only form the one isomer. Now, if instead of this weaker base, we had chosen a T-butoxide, like this one right here, as our base for this reaction, that would go E2. Perhaps even if we had just hydroxide in there, we would definitely get some more E2 products. That said, we would still have a lot of selectivity. We wouldn't change the different products. It wouldn't be a different product just because of there's no chirality on the other carbons here. And so because of that, we're not going to increase or change our selectivity really much. So it's one of those cases where the mechanism might not matter as much as just knowing that it's an elimination. All right, so that's some examples on how to decide which direction a reaction is going to go. You really need to add up all of those factors that I brought up in the beginning, and you can use those as like a point system to help you decide, oh, this one's getting a lot of points in the column that, you know, would indicate this is going in SN2 or whatever direction it is. Then you can use that to help you decide which direction the reaction will go.